My GCSE grades were terrible. My A-level grades were predicted to be terrible. The ability wasn't the issue. It was the enthusiasm. It was the drive. To sit down. I think it's a bit stark. It's a bit real. But the best mathematicians I know are the ones who have kept on going.
Hello and welcome to the Knowness podcast, the vault of knowledge. All right, Alex, would you like to introduce yourself?
Cool. So yes, my name is Alex. I am the subject maths lead for Knowness, and I went to Durham. I studied natural sciences up there, and I did, again, primarily maths modules. With like a really amazing set of lecturers. And during that time, I kind of really got into the applied stuff, and now I am here in this amazing room with two amazingly funny guys. You can't. You're already ready to start laughing.
Kind man, kind comments.
And yeah, there's so much to do with maths. It's one of those subjects where I like to call it like this kind of giant in-joke, in the sense that people who do maths know what it's about, but they find it very difficult communicating it. It's almost universally bad across the entire field because, you know, it's one of those things where you study for so long that you forget what you don't know. And then when you meet someone who doesn't, know as much as you do, you struggle to tell them.
Like explain it and stuff.
Yeah, exactly. Like,
I even mentioned last episode when you came on about like science communication.
Yeah.
And like, I guess like, literacy when it comes to, is that a thing, mathematical literacy?
Yeah, absolutely.
Guess,
you got to like know a field, and you got to like know people in that field. Yeah. Especially like the higher level, like for like, I guess, research. Yeah. Which I'm hoping to get into by PhDs and all that. Yeah. But yeah, it's one of those things where it's like, there's so much to it, and it's so hard to explain because all it does is build up on itself each year. It's not like English where you can
pick like a
play
pick
like whatever you want, and I might be completely wrong about this. Yeah. If I offended anyone else out there, I'm sorry. But yeah, so that's kind of like really drew me here. Yeah. With Knowness is that.
Would you say it's like sorry to interrupt?
No.
I remember I used to interrupt this guy a lot. So no, because I feel like it's always medicine, right? That's the one I can speak on because that's my background.
Yeah.
I feel like you can very easily categorize it, and so when it comes to speaking about medicine to someone else, it's easy because those categories are already there. And I feel like is maths, is it kind of like that? Or would you say it's just there's nothing? How would you describe it?
I always say it's like climbing a mountain. Yeah. Or like a mountain range. So like everyone starts at the bottom of the mountain. They study like the calculus courses, the linear algebra. Yeah. And you go up. So like, maybe by second year you start doing your pure courses. You might go into algebra, rings, fields, modules, and representation theory, and whatever that is. So you're slightly higher up. And then third year, maybe that's when you start doing some serious maths. Yeah. You might have quantum mechanics here, but you might also have Riemannian geometry, and yes, completely different things. Yeah. And you might even go further. You might start going to numerical analysis, which is just a different mountain range entirely. Yeah. And by that point, after 4 years, and this is just on the graduate level, you're going to have people who are at the top of their mountains who just can't talk to each other about their own fields. Yeah. They can understand or learn the tools to understand what's going on elsewhere, but that's going to take maybe a year.
Yeah. So I'm really interested to know. So you did natural sciences. You didn't do maths at uni.
I was going to ask that.
So yeah. So how come you decided to do natural sciences and then maths? So why did you get into natural sciences first?
Natural sciences is the degree for people who don't know what they want to do.
Okay, cool.
Maths, physics, chemistry is the A-level choices for people who don't know what they want to do.
Yeah, literally. Exactly. It keeps everything wide open.
Exactly.
Yeah, exactly.
Yeah. And also, it's been kind of nice when I was my first year, I had the option of switching to straight maths or straight chemistry. And I honestly think, as an 18-year-old, I was not equipped to make that decision.
Well, that's why we in Knowness have a careers program where we have taster courses, which you're working on right now.
Yes.
Where we help people, decide what degrees they want to do at university.
About knowness.com.
No, but genuinely, that's one of the big draw here because I didn't have that, and I got lucky. Yeah. Right? I got a good set of A-levels. It was STEMmy, at least they're linked. And I got a good degree in subjects which I did want to do. I remember my second year when I was doing chemistry during COVID. I was
second year of your degree, you mean?
Yes, second year. There was some thermodynamics lecturer, and they were talking about how the rate of reaction can determine the amount of product you get. And I just sat there on Zoom thinking, I don't give a crap about molecules. And then followed by like, oh dear, I'm doing the wrong course. And yeah,
Kinetics right there.
yeah.
Yeah.
And I mean, I look back on it now and think, well, I'm kind of glad I went for it. I have something to say about. I split interdisciplinary. I can say I took a look at chemistry and I've done a maths degree. Obviously, it was a lot harder because there were gaps I had to fill in. But I think breadth, especially in the stuff that I'm interested in, is very, very useful. So I'm looking to go into mathematical biology, and that's, to me, that's amazing.
Yeah.
How does maths and biology intersect?
That's great.
That's really
Yeah, I didn't even think about that. Yeah.
So let's go back. But at what point during your degree did you decide I'm going to do maths? Like, what was it?
Was there like a set moment?
Did you do
like
a
gradual-
module that was like very maths heavy? What happened?
Was there a module? I mean, I think it was very passive. I did maths because I use it as a tool. I thought it could be a useful tool to apply to systems like chemistry, like the kinetics, like the kind of physical chemistry you get, like quantum mechanics. And then when I realized I didn't like chemistry, I went, well, maths is the one that I've stuck with all this time, and well, maybe I liked it all along. I think the one module I actually did like the most was math bio in my third year. I saw it in my first year and thought to myself, no way that exists.
Yeah.
And then my lecturers in my third year, absolutely incredible.
Well, what is it? Mathematical biology.
Math bio. What is math bio? If I ask you a question like, how does a leopard get its spots? Is it a leopard or a cheetah?
Both.
Both.
I mean, cheetah have spots. No, both have spots.
Wait.
Yeah, both leopards and
leopards.
cheetahs. They're two different
Snow
species.
leopards have spots.
Yeah. And
No,
panthers
normal
are black.
leopards also have spots.
Panthers don't have spots.
Panthers
panthers don't. They're either
Wait, hold
black
on.
or they're pink.
No, panthers is not a species. Jaguars are a species. Panthers are a type of jaguar. Or they're like a coloration.
The more you know. That's all right.
No, but jaguars also have spots. You just can't. Panthers also have spots.
Let's pick a different animal.
Let's make someone
You
else.
just can't see them.
Hey, what's animal with spots? Like a ladybird.
Ladybird,
Or
yes.
like a cheetah.
Yes,
Yeah.
that's a good
Cheetah.
one. Yeah.
Oh, they do. The cheetah guy.
Yeah. Cheetah guy.
That's what I remember.
That's actually my first reference in my dissertation was a children's book.
Was it?
It was how the leopard got its spots.
Oh, yeah. That's actually a book in it.
And then my second reference was Alan Turing's paper, which created the entire field.
That's
Alan
mad.
Turing had a paper
What a
on
jump.
mathematical biology.
He wrote it on what's called the
Wait,
chemical basis.
hold on. Nassim, do you know who Alan Turing is?
Hey, I know. I made a post about this on the Knowness Instagram.
Okay, good. Just making sure.
He's the computer science guy.
Yeah, could you explain first of all for our general audience
test.
who Alan Turing was?
Alan Turing was a computer scientist, began as a computer scientist during World War II. So he was the main guy behind the Enigma machine,
Yeah.
cracking the codes.
He did the Turing test as well. That's not a
Turing
movie.
test.
Yeah, wait, hold on.
So that's for.
So could you expand on what the codes were? Because again, not everyone knows about this.
So when the Germans were communicating with each other, they were encrypted, obviously, because they didn't want the other countries to
know what they're saying.
The messages were encrypted.
Yes.
Yeah.
Because at that time, information was victory. If you've seen Operation Mincemeat.
No.
No, I've
Sounds
seen the
very
Enigma machine.
interesting.
Well, that's probably more relevant. Well,
Yeah.
exactly. I'll go into Mincemeat because I watched it in
okay.
West End. Brilliant show, hilarious. But the idea behind that is it's information warfare, and they were trying to save the lives of British troops and end the war as quickly as possible. And by knowing what the Germans were talking about and their plans, then it'll give us an upper hand. So Alan Turing worked with a team of people at Bletchley Park to decrypt the German communications by creating the Enigma machine.
Yeah.
And I can't go into the details of how they do it. But I think the time it would take to brute force the German encryption if they had had to guess the basically code 10 times every single second, it will take about 200 years.
Damn,
Or it's something instantly long. I can't remember the exact
They were
same
gonna
number.
brute force it.
So it just wouldn't pass. So they had to be clever, and they use things like if there's a weather report and they knew they were talking about, say, cloudy skies.
Yeah.
They knew that what was being translated was to do with cloudy skies. So there was probably some link there. They could pick out certain words and certain letters and get someone to.
So they are linguists as well as mathematicians working on cracking the code.
And finding all these links and connections and then using that to narrow things down, basically.
So that's what we know Alan Turing for breaking the code. But then not long after that, he wrote a paper. He had an amazing intuition for this on what's called the chemical basis of morphogenesis, which is basically you ask yourself a question: how can we describe mathematically how we get the spirals on our fingertips or the wrinkles on our forehead? Or like I said, spots on a cheetah.
The Cheeto guy.
Yeah.
Or a leopard.
Or a leopard.
jaguar.
Or a leopard.
Yeah, or
And
lion.
it was a really great paper he wrote because he wrote it for biologists, chemists, and mathematicians. So
Yeah.
like it was very broad, very kind of varied, and that kind of kicked off the math bio field. It's cited pretty much in every single paper. Absolutely, like one of my favorites. It's one of the few papers they give you in your undergrad where they actually expect you to be able to read it and understand it.
Yeah.
Because it's just a pleasure to read.
Yeah.
It has plenty of good history, and the key part for that for me is that this man had this incredible intuition about this really weird, like hard to grasp concepts about what we call these partial differential equations. And university courses might take a year or two to like really go into what these PDEs are. And this man just gets it. It's like, it's perfect.
Yeah.
He writes in a paper with no numerical aid, no computers to solve these equations for him. He has to do things by hand.
Yeah.
And he produces an entire field
That's crazy,
after saving, the world.
Yeah.
the man didn't stop.
Yeah, literally, yeah.
It's on the pound bill, isn't it? No.
Yeah. Is it a £5 note? Is it?
Something like that. Yeah.
Didn't get done over by the government.
Yeah, he did. He was chemically castrated.
Poor guy.
I guess we don't have to get into that.
Yeah. It's a real shame. It really is a
That's
real
actually
shame.
pretty sad.
But at the same time, I like to say is the reason I'm here right now. Like my interest in like math bio kind of really got me going. I started reading around it. I worked on.
Sorry, I was going to ask, what are some examples? What are your favorite examples of mathematical biology?
My favorite examples of math bio. Oh.
Yeah.
Because I can think of it. So I think the first one that we usually learn about is usually the golden ratio.
You do math bio?
No, just like in general, you see the golden ratio in nature. That's something you see on the internet. A lot of times it's like flower patterns, stuff like that, or like shells, for example.
This is a good one.
Ratio.
So it's kind of like a misnomer.
Sequence. Yeah.
The golden ratio doesn't actually appear that much. It is just a popular science thing. But there are some really interesting like models I've seen. And one of them is like a Clausimeyer vegetation pattern. And it's literally just vegetation patterns on like plains and kind of predict like where you might see growth of wildlife. Was it flora or fauna?
Flora is plants.
Plants, yes. And they come up with a like really nasty looking model, and they kind of solve it and say, yeah, okay, you run it, you'll predict to see seaweed growing here. And it's like, what? How'd you get there?
From there to there.
From FIO. What's my favorite example though? See, it's not just math bio this is useful to. It's useful in like quantum mechanics.
Yeah, exactly.
All sorts of dynamical systems.
Yeah, so this is the thing I think is really cool about maths. You see the same patterns emerge at all levels of theory, all levels of life and the world. But I don't know. It's like, why does that happen? Like,
why does that happen?
Ooh, that is a very, very.
Why does it happen?
Question.
You know what I mean? Like that's what I always wonder. That's
question.
why it's like, why? It's like it seems, I don't know. It just seems insane to me.
Yeah.
Maths is also the study of isomorphisms.
What is isomorphism?
That's another way of saying things which are equal.
Okay.
Quite a roundabout way of saying. So if we knew the answer to that question.
So when you say an isomorphism, so is the golden ratio in a shell the same as the when you say the golden ratio in a flower, let's say? Is that two isomorphs?
What I'd say is like, that'd be a bit more abstract. So let's say counting 1 + 2 + 3 + 4. We're used to how that works.
Yeah.
But if you start counting on a clock, so you do 1 + 2 + 3, that takes you to what 1 + 2 + 3 is 6.
Yeah.
But if you do 10 + 3 on a clock, that's not 13, that's 1.
Yeah, because it's 12 hours.
Yeah, exactly. It's like cyclic.
Yeah.
So it's kind of an isomorphism. We can construct like a map between this, like this, 1 + 2 + 3 and so on, to, let's call it clock addition.
Yeah.
And we can do a map backwards, right?
Yeah.
Can we do that backwards? Let's ignore I said that.
No worries.
But yeah, it's basically, this is what I'm saying. We've got two different things, and I'm telling you they are equal in some way. I can say, let's do something more abstract as well. A donut.
Yeah.
Lovely thing. The shape of a donut
I do like donuts.
is the same as a mug.
Yeah.
Yeah, I've heard that a lot.
Yes, it's a very famous example.
Yeah.
Wait, what do you mean it's the shape of a mug?
Okay, how many holes does a mug have?
It's got one.
How many holes does a donut have?
One.
How many holes do your trousers have?
3.
No.
I swear it's 3. Is it not 3? Oh, 1. Because technically it's like 1.
No.
What? It's like a riddle. 2.
It's 2.
Just 2 holes.
2 holes.
One for each leg.
Oh no, I'm thinking at the top.
Yeah, but to be fair, so it's like one
It's like
opening
1.
that goes into
Oh,
2.
okay,
Yeah.
So he was saying a donut and a mug are the same,
Yeah.
but your trousers
But
are
they're
not the same
not-
as a donut.
So there are
gotcha.
isomorphs. Is that what you would say?
So
That's seen by isomorphs.
you can say a donut is topologically equivalent to a mug.
Okay,
and
so
then
they're
you
the same in that one sense.
What would you call the differences between a mug and a donut? Why are they different?
So they're geometrically different.
They're geometric. So that's how you define it.
Yeah. So then there's topology, which we're going to get, that's like smooth deformations of objects.
Yeah.
And then geometry, which is, I don't know how to describe that one. But
Yeah.
yeah, again, it's another example of things being the same but actually different.
But actually not the same, yeah.
And like, it's a really fun example I had in my dissertation where I was saying that, like the water on our table, it is still right now.
Mm-hmm.
But if I perturb it, like I flick it can do 2 things. It might stay in the mug, it might stay in the cup, or it will come flowing out and you'll be very upset for making a mess.
Yeah.
So that's what we call like a dynamical system, right? And I was studying these long-term properties of these dynamical systems, and I was saying, well, what happens when we consider them on something which has symmetry? And suddenly now some interesting things start happening. So you're taking
Say again,
symmetries.
sorry, go back. So I didn't get that last part. What happens when what?
When we start looking at symmetries
When we look-
as well.
okay.
So not just the like the dynamics of what's happening to the water in the cup.
Yeah.
Let's say what's happening, what's interesting about the cup itself. And like we can see, it's like pretend it's a cylinder, right?
Yeah.
Nearly.
Pretty close. It's pretty close.
Close
Yeah.
enough, close enough.
It's got like a circular symmetry. We can rotate it, it'll still be the same cup.
Uh-huh.
We
Yeah.
can reflect it, it'll still be the same cup.
Yeah.
And I was looking at things which were like, how do the dynamical systems that they're studying, how are they impacted by the symmetry of the objects that we're working with?
Yeah.
And you can do a bunch of maths and show that, look, guess what? It's the same thing.
It's the same thing.
Kind of hand wavy there. Definitely not the entire truth.
Yeah.
I think it's enough.
Still, yeah.
Mm-hmm.
Damn. It's like that scene in the interview where it's like same but different, but still same. It's basically like that. Yeah. That's really interesting. So would you say like when it comes to maths, your primary interest is mathematical biology or?
But that's very broad, isn't it? 'Cause
It's
a
so
lot-
huge.
yeah, that's
there's
the
a
issue
lot of
with
different
maths. There's
areas
so
of maths
much.
that would come into biology.
Too broad, yeah.
Yeah, I mean, there's oncology, there's ecology.
Oncology.
Yeah, so that's cancer.
Here's
Oh,
medical-
Are
the
you?
medicine.
But yeah, I was gonna
working
say,
for-
yeah, I guess that, yeah.
I thought oncology.
I thought oncology is like another word for something in the hospital for a second.
yeah.
yeah.
No. But I mean, it's wild. There's like what's called like blood vessel formation as one of the other things.
Yeah, as part of the mathematical biology.
And,
Yeah.
And then there's this general pattern formation. So like the ones I was describing, like
Yeah.
these. So one of the projects I was looking at was like this dendritic cell clustering in patients with cancer.
Yeah.
You're like, well, patients who have favorable outcomes have a certain type of formation of dendritic cells in like certain parts of the body. Like, how do you do that? So, the question itself asks is, how do you prompt that kind of formation?
Yeah.
Is there a treatment or an immunotherapy treatment that you can devise
Target
to,
that
yeah,
formation.
which that, and
Yeah.
obviously get favorable outcome for cancer treatments.
Yeah.
And it's like, what?
That's crazy, yeah.
All sorts of things.
I think that's the thing, yeah.
And they do like agent-based modeling. So there's a bunch of people in Oxford who do this. Oxford started off as like the center basically for MathBio because of James Murray, who wrote basically the book on
Yeah.
it.
Is it the one with the tiger on it?
It's got a leopard.
I thought it was a tiger. I do recognize the book when you.
It's quite green.
Yeah, it's very green.
Close. And
Felines.
This would be the title of this podcast, just talking about felines. The cat podcast.
Yeah. No lions? No.
Yeah.
No.
Excuse them in. Lions don't have spots. Yeah, they don't have spots.
No,
No,
they don't have
they-
spots.
They do?
I don't think so.
I don't think they do now.
don't,
No.
I don't go outside enough.
Zebras,
to
though.
see them.
Zebra
Zebras,
patterns
they have
on
stripes.
zebra.
They have stripes,
Yeah, they have
yes.
stripes.
Yeah. Oh, wow. What are
Nah,
they?
they don't have spots. I remember the lion from Madagascar.
Oh, what?
Okay.
Wait, what?
Alex, same name as you. The lion
Oh,
from
yeah.
Madagascar. Yeah, no spots, no spots. Okay. Lions, no spots. Okay, but so, okay, when it comes to... back on track,
Thinking.
yeah? When it comes to, your career, like long term, is mathematical biology like what you want to get into? Or
Absolutely, like fully plan on doing a PhD within like that field. And there's so many like amazing researchers. So
is it mainly research? Like, is that what that kind of field looks like career-wise?
You know, I really should know. I've only been looking kind of short term, which to me looks 4 years ahead.
Yeah.
I think the option is like you can stay in academia, either within universities, which is quite hard and quite unlikely, or go into industry, like AstraZeneca, for instance. They employ math bio. They use data science tools basically to do some of their work. It's a very broad church of subjects, and I think I'd really only truly know what I want to do and after I'd complete something, after complete like doctoral study. Like at the end of the day, it's you talk to people, you find out what they do, and you really do love your subject. But sometimes, like at this stage, you just admit like I don't know, and that's what study is for. That's what post study is will take me to, which is really kind of exciting.
Yeah, it is. Seeing where it takes you, because these kind of what you're doing is kind of opening the doors, many doors, and then just wherever it takes you, it takes you.
Just at least doing good. I think.
Definitely.
The ideal aim. I'm not in finance making a billionaire richer.
Yeah, no, I didn't know you could use maths.
You could be with your math skills.
Yeah, you could. Yeah.
Sorry.
So tell me something. So what advice would you give to someone who wants to get into maths, like a uni or maybe even PhD level?
To get into maths,
Would you say you need to really require genuine interest in it, or
it's hard to say. It's you gotta want to do it, obviously. But it's not the same as like passion isn't just enough. It's having that like grit. It's being able to be stuck, accepting that you don't know, knowing that you can reach out, forming connections and talking to people. The one thing with maths is that any serious researcher, so I'll speak on behalf of every single professional mathematician out there who has completed a PhD or done work, with probability 1, they have been mentally ill at some point, because it's one of those subjects where you can become kind of isolated. And you become the only person in the world who knows what you're talking about. So you find it difficult to talk to other people. And obviously, you can see where it follows. So it's got to be that sub. Like, you got to have grit. You got to be willing to like understand you're not going to know everything, and you got to accept like, okay, I'll put my hand up. I will be stuck, and I will work through this. And it's okay not knowing everything, because right now, like this is the best I can do. If they have that, I think that's more important than just enthusiasm. Ability is tertiary. I couldn't read until I was 7 years old. I was in the bottom set of maths for however long at school. My GCSE grades were terrible. My A-level grades were like predicted to be terrible. But again, the ability wasn't the issue. It was the enthusiasm. It was the drive to sit down and want and be willing to suffer. I say suffer, and it kind of like it's not work. It's like a challenge. You got to have the mindset to overcome it. I think it's a bit stark. It's a bit real. But the best mathematicians I know are the ones who have kept on going. Like
so like resilience is the big
and discipline.
Especially true for PhDs.
And it's inspiring, but in a way also kind of scary. Like losing yourself in maths and not really being able to find people that understand and like are in the same like kind of like field, or what's the word? Do you know what I mean? It's very different from like other subjects or careers where you'll be, there's the isolation isn't really there, and they're more like collaborative. Their jobs, like for example in medicine, you're always going to be in a hospital. You'll be seeing people. It's very social. Do you know what I mean?
Yeah, here's the other thing about mathematicians: they suck at regular person chat. Right? They are terrible. I went to a bar crawl my first year, and I didn't speak to them for 3 years after that. I was doing everything that I said don't do, because they went to the bar, then they spent 20 minutes at each pub. Saying nothing to each other. They went to the
no maths jokes or anything.
I was awful too, though. My freshers week, I played a really fun game of, hey everybody, let's solve a differential equation. Each line we get wrong, you drink. I made no friends.
Just straight maths.
It was awful. So be passionate, don't be weird.
I think the isolation is true for research in general, like in any, especially in STEM though, because again, as you said earlier, you become the world leader in the one question you've been researching for the last 20 years of your life.
Yes.
And you have no one to talk to about it, basically.
Do you know why people are so enthusiastic about subject?
Why?
It's because they finally get a chance to talk to them about it. And
exactly.
I'm holding everything back not to talk about Visual PDE right now.
We can get into that if you
Okay,
want.
we get into it.
But would you say the hard work at the end of the day is worth it? When you say so? So that's sort of like the light at the end of the
your
tunnel.
field where you're actually doing good.
You can see what you've done. You can see how far you've got. I mean, I ask you, 5 years ago when you started university or you left school, you look back to what you knew back then and what you know now. First thing, like you changed as a person, I'm sure.
Yeah.
But also what you know and the kind of way it's maybe changed your mindset. Like that is something you can reflect on.
Yeah, definitely.
Sure, it took 5 years.
Yeah.
I mean, I wanted to quit halfway through my master's degree because of like COVID didn't help.
Yeah, it's just extra isolation.
Yeah. It's just one of those things where, you're alone, but it doesn't have to be alone. The best researchers I know are the ones who can talk. And then because they're funny, everyone loves them. They'll invite you around for a tea. You know.
Yeah, it's just good vibes. You know what I mean? So I guess bouncing off of that as well, when it comes to, I don't say like work-life balance or like study like life balance. What does that look like for you? And what advice would you give around that?
Do you mean like at A levels or?
I mean at university level and beyond.
Yes. Okay.
University A levels as well. To be fair,
actually,
I feel like it applies across the board.
I think for A levels, if you're trying to do well in maths, it's do the past papers. Do every single past paper.
Yeah. Well,
big thing.
We had a problem.
When
we started doing A levels, they completely changed the syllabus.
So we had no past papers. We also had OCR MEI, which was not fun.
Don't get me started.
We had like a comprehension paper.
It was traumatic.
It was straight trauma. I genuinely have PTSD.
The audience doesn't care about this.
No, we're protecting them to stay away from
A levels
OCR
at GCSEs, past papers is where
do
it's at.
every single past
Exam
paper.
technique is everything.
Learn to write down your thoughts. If you're not having thoughts, then figure them out.
Ask your teachers.
Yes, that's what they're there for.
It's the time in life where you have the most availability of teachers. When you go to university, you can't just ask your teachers every day for questions.
I think if your lecturers dislike you because you're asking too many questions, you're doing good. Because they don't actually dislike you. They're just thinking, oh my God, I've got an enthusiastic student. Obviously, I didn't go to every single office hour. I needed to. But I didn't know what to ask. I felt like, well, I haven't done enough to actually bother asking, so maybe I'll just leave it till next week.
I mean, the barrier of entry to go and ask a supervisor, a lecturer, is way higher than school. They're not just there in front of you.
Exactly.
You know what I mean? That's the problem. You have to go out of your way.
To find them.
Plan it out. Put a meeting on your calendar.
Contact them, email them.
Exactly.
Kind of stuff.
Study, but generally study things. It's very specific to each individual, and I can say what worked for me, but I know that it's not the same as what everyone else did.
Still,
I don't like knowing things. I like being able to figure them out. Because I am very bloody lazy. So I would have some sort of like, okay, let's go for there's something in general relativity, something about how some indices operate on each other, how these tensors operate, and you have to memorize some basically like index manipulation. And it's a pain in the ass if you just memorize it. If you learn how to actually do the operation, contravariant and covariant indices operate on each other, then you get like a nice kind of ish theory that you can work with without having to just memorize this transforms like this, which transforms like this, so this can do that. And
that's very helpful in the physical sciences because you can really learn how everything works if you work from first principles. You can just make it up yourself.
And I this is kind of a bad thing though now because it translates to what I do regularly. Like if I think something can be done, like can be done in my head, it's already done. I can make my bed. It's done.
I've already solved it. I know I can solve it.
I know how to do it. It's done.
And then that's it. The main thing for you is just knowing how to do it. That's it.
And then because it's like when seeing an integral, right? I know how to do the integral. Done it. I won't actually do the steps. And they'll be like
around it, but okay, so
I was gonna say So I was gonna say, okay, so there's a demographic of people who everyone's met who detest maths, who are maths phobic, don't want to know about maths. And I always think they just don't quite get it. What's interesting, they just think it's just maths is only used to like calculate your taxes
And I feel like you just pull out a calculator.
And yeah, exactly. Just pull out a calculator. That's
Stick a
it.
calculator out, yeah.
What would you say to them?
What would I say to them? I met one person like this, and I asked
I met a
them.
lot of people like this. But sorry, carry on.
I mean,
I am that person, yeah.
yeah.
No, this is interesting. And what I said to them was, pick something in this room, and I'll tell you how maths has influenced it.
Ooh, okay, it's lamp.
Okay.
What were you going to say? Oh, wait, the microphone.
Well, there's literally a telescope over there.
There's a telescope. Well, that's too obvious.
Okay, it's too obvious.
Is it?
Well, there's a boat. There's a lot of like fluid dynamics going on there.
Yeah. Well, you're already answering your own question.
Oh, yeah, I know. Sorry.
go.
Well, I don't hate
Okay,
maths.
let me think.
You think?
You go for it.
The plant? Behind me?
The plant. We are talking about math bio.
Yeah. Okay.
What about the globe?
The globe. Oh, okay, that's an interesting one.
Okay, let's do the globe one. Yeah.
You see the globe here. Let's look at Greenland.
Yeah.
Wait, you can pick it up.
Yeah.
Just grab it. Yeah.
Just be careful.
Wicked.
Ooh.
Let's
Yeah.
see Greenland and Africa. See
look.
how small Greenland it is?
Yeah.
It's tiny.
Yeah.
See how
right
big-
at the top there.
Yeah. See how big Africa is?
Yeah.
Yeah.
I'll do it for the viewers at home.
Okay.
Big Africa.
I think that's the other way around. You meant to say that Africa is small and Greenland's big.
Well, on
Wait.
the maps that we have, I mean, Greenland is tiny.
Yeah.
Yeah.
Oh, yeah. You're
From what
right.
we see, it's tiny.
Yeah.
Yeah, and the reason for that is for something from what's it called? Geometry.
Yeah.
It's curvature.
Uh-huh.
And what you see on a flat image on a 2D map, right?
Yeah.
Which you put on your wall,
Mhm.
on certain what we call projections, Greenland is massive, right? Remember
Yeah.
how big it is?
But in the normal ones that you see, that 2D one,
Yeah.
Greenland is almost as big as Africa.
Yeah,
exactly.
But then,
Yeah.
Africa is quite a bit smaller. So not only does Greenland get huge, Africa gets tiny.
Yeah.
And the reason for that is that there's a topological quantity which we're not preserving under the transformation from a 2D, a flat thing,
Mhm.
to a sphere.
Gotcha.
And this is one of those things where I'm saying that isomorphism thing again.
Yeah. Where it's
the
like it's the
square
same.
is not the same as a sphere because the square is 2D, right?
Yeah.
Yeah.
But this is 3D. It's a 3D shape.
So it's the same thing as in it's a 3D shape, but
yeah.
Okay.
it's not the same thing.
What's the relation between a circle and a sphere then?
A circle and a sphere.
Uh-huh.
I guess if you rotate a circle, then you get a sphere.
No?
Do you?
I guess.
Or if you rotate a circle, like, no, you don't.
If you rotate a circle, you still get a circle,
No,
don't
you-
you?
Hold on, am I thinking this correctly?
Because I mean, there's a relationship between a cube and a
It
square,
sounds like an interview question.
doesn't it?
Cube and a square.
Yeah. I mean, the
Well, like a
faces of a
projection.
cube. Yeah.
Oh, are you saying so you can project? Yeah, you can project a.
The shadow of a sphere is a
Is a
circle.
circle, yes.
Yeah. So that's what.
There's a fun thing about something else. No,
Don't worry.
No,
don't
no,
worry.
I
Too
won't
much
go
maths
into
for my brain.
Yeah, too much math.
but yeah, the point
that
about
is
this was
interesting,
that you got these two
You're not considering the topographical, topological
quantities which are not preserved
Yeah.
when you do these
when
transformations.
you change it to a sphere.
And that's might not seem very interesting, but it
Yeah.
answers a question, right? Here's a good one. When you're flying, say you're flying to the US, you see
Yeah.
that the plane, the arc, go over like a curved
Yeah.
line. You think to yourself, why is it not going straight? It'll be so much faster if it's straight.
Yeah.
Funnily
Yeah.
enough, this isn't flat. Controversial sometimes, but it's actually taking account the curvature of the Earth.
Yeah.
But when you're doing that over 2,000 kilometers,
Yeah.
then you have to have a curved line on a flat surface.
Yeah.
There you go. On this sphere, it looks like a straight line,
Yeah.
right?
Yeah.
But on
yeah.
a flat plane,
It's
a
actually
curved
a lot
line.
more exaggerated than you think. It almost looks like an arc when
Yes.
you see it on
When
the
planes
thing.
are traveling, it's like
yeah.
that kind of.
It looks
okay,
like traveling on an arc.
It's
The thing
not going
is-
straight as
I mean, it is flying straight.
yes,
That's-
it is
yeah,
flying
but-
straight,
yeah.
but
Yeah.
on this projection, it looks
it would be
curved.
a curved. Yeah, I know what you mean. Yeah,
exactly.
But it's just
Interesting.
in one direction. Yeah.
And what's cool about that
interesting,
as well is that if they go straight, we're flying through the ocean.
Mhm.
Yeah.
You're
Yeah.
like, it's got your sphere here. You'll be cutting through it.
Yeah. Exactly. Yeah. Like if it was like from like top of Africa going straight, you'd be flying towards you.
Yeah.
But in reality, it's going around. That's interesting.
Yeah.
That's in every aspect of life. But kind of similar to your question. The next question is, it may seem like a basic one, right?
Mhm.
But like, how would you like if someone says to you, "What's maths?" How would you define it in your own words? What is maths?
I really
it's-
struggled with what is chemistry.
Yeah,
Like,
yeah,
really,
yeah.
like,
And that's chemistry, right? But with maths, like you mentioned, there's so much to it.
it's a bit more abstract. I would
definitely.
assume. Yeah.
There's should do it like that Genius video. The explaining to a toddler to a 10-year-old.
Yeah.
used to
Yeah.
see.
Yeah.
So I say to a kid,
Yeah.
so my 11-year-old niece, I tell her that maths is the study of patterns. She doesn't care. She likes listening to Taylor Swift and Instagram Reels, but like I'm gonna make her an academic weapon one day. So, but she's only 11 years old, so it's acceptable.
It's all right for now.
And then so that's why I say to young children, it's a study of patterns. When you get kind of more advanced, well, I like to say, what is the most ridiculous thing you can say while still being true?
Oh, don't ask Nassim.
Don't ask me.
What is the most ridiculous thing you can say while still being true?
Yeah,
you have to bleep us and stuff. But that's a nice way of saying the definition. Yeah,
like coffee mugs and donuts.
Yeah,
no, it's stupid. I mean,
it's ridiculous, but it's true.
It is.
It's
true. It is fact.
They are like the same in that sense. Yeah.
And then when you get higher and higher, I say it's a study of isomorphisms.
Oh, isn't everything? It's okay.
Yeah.
But that is a fancy way of saying patterns, isn't it?
I say patterns as so you're seeing quantities and you're linking them together and you're saying, they're actually equal. And then again, I'm missing things are equal in different ways.
That's an isomorphism.
There we are. I think it's a beautiful word.
Isomorphism.
There's some words in maths which have just ruined for me, like group. Right?
Group,
Why?
Because group theory, and I think I did group theory, and ruined. Calculus. Didn't realize calculus was a real word.
What do you mean?
Is it?
What do you mean it's a real word?
It actually means something not just like differentiation, integration.
Does it mean like calculating?
Yeah, like his calculus. Or
it's like computer, like computing something.
Oh,
used to mean to just like work something out.
Computers computing.
There's so many. Representation.
Yeah.
Also
representation.
A word.
That's part of group theory, isn't it? Yeah. So actually, because group theory, you mentioned symmetry earlier, and that's something I'm really interested in chemistry. Could you? I really like you because it links with the quantum mechanics that I did in my course. Could you really explain to like a general audience what group theory is and how symmetry and representations,
we're using this
and
as like
maybe
a
even
session.
quantum mechanics eventually
this is
links
really
together?
good
Because it's so interesting and it's something I feel like everyone should know a little bit, at least a little bit about.
I think everyone should know about representation theory.
Yeah,
100%.
It's a shame it's not taught.
I've never heard of representation theory.
Okay, well you're like a test subject now.
Yeah, exactly. That's why it's here.
That's a dummy test subject.
So what's great?
Test dummy.
Let's view. Okay, I'm going to.
I wish I had my molecular kit here. That'd be so good if I had it in hand.
Don't give me started. I love them.
What is it? Molecular kit?
It's just like that thing that you make your molecules, like a little thing.
I was never given this
you
toy as a
had
kid.
them in school,
we
man.
needed better hobbies.
Yeah.
I got like Ben 10 figures, but not.
All right, carry on. I'm really interested.
Let's go. So let's look at we've got a finite group because it's got a countable number of elements. We're going to look at the symmetries of a square. And I'm going to tell you there's 8 things that you can do to a square, like a perfect square. Like imagine this.
I feel like you should start simpler. Like what are the symmetry axes of symmetries on a square, or like lines of symmetry?
Like one. What's it?
So you can reflect vertically,
vertically, horizontally, diagonally.
So diagonally. So how many is that?
It's 1, 2, 3, 4.
Yeah. You can also rotate the square.
Okay, and then do it again. 1, 2, 3,
That's a different operation.
Yeah.
So these are reflections. These are rotations.
Yeah. Exactly. And so you see where I'm going with this. I'm saying there's also one density which we've got out. You can do nothing to the square.
Yeah, but that's the element.
Exactly. So what I've done there is I've constructed a group. There are some axioms which actually define a group, but I won't go into them. But one of them is saying that if I do a reflection followed by a rotation, that is actually equivalent to another element in the group. So if I do 2 rotations, so I do rotation 1 by 90 degrees and rotation by 180 degrees, that's actually the same thing as doing a rotation by 270 degrees.
Gotcha,
and that element is in the group.
Yeah, so there's a finite amount of symmetry.
Yeah, of operations you can do. And what I think is quite useful in chemistry is you can start applying this theory to certain molecules. So a molecule, it might be like square planar, right?
Yeah. He doesn't know what that means. Do you know what square planar means?
Yeah, it's like on the. It's like a no.
Would you explain what square planar? Well, okay.
It just mean like a flat plane.
Give an example.
Yeah, let's go back to groups, groups, and why they're important. So you see all those operations we mentioned there.
Yeah.
So 4 reflections. How many rotations is that?
3.
3 rotations. So any other object that you can also apply these operations on, 4 reflections and 3 rotations, are all part of the group that squares are part of.
They're the same thing.
Oh,
They're the
I see what
same.
you mean.
It's an
Okay, yeah,
isomorphism. There you go.
Oh, okay, it's
So all
isomorphs.
groups.
Anything you can do that with.
But
It's like triangles.
yeah, so every object you have, you can
Yeah.
define it by the operations you can do by their symmetry essentially, and then you can put them in different groups together. So
Okay.
a pyramid is a different group from a cube. A cube is a different group from a, I don't know, some more complex looking object. A sphere.
But
is in a
triangle would be the
complex-
same as like the square.
No, it wouldn't.
Can you rotate a triangle by 200? Well, no,
Okay,
180
no, but
degrees.
how many axes of symmetry does a triangle have?
Oh, so it's okay. So it's not the same axis. That's why.
Yeah,
it's
exactly.
different.
But how many does it have? Count them.
It's one.
One. If it's a, it depends on if
Two.
it's an equilateral triangle.
Yeah.
It's got one, two,
two,
three. How many
yeah.
did the square have?
So I had was it 1, 2, 3, 4?
Four, exactly.
Okay,
So in a
it's
different
in
group.
that sense. Gotcha,
Exactly.
gotcha,
But
gotcha.
all objects have 3 axes of symmetry, and
They all and
a
flat.
C3 rotation, so they can be
Yeah.
rotated 3 times.
He doesn't know what that means.
Yeah. Oh, so sorry. Or like you can rotate. So you can rotate a triangle 3
Yeah,
times,
Yeah.
and you get the same
yeah,
shape.
You get this, yeah.
Yeah, you get that. You get
yeah,
that.
yeah.
So all of them are in the same group as a
Gotcha,
triangle. So it's a
okay.
way of categorizing
Anything
all
that
objects.
comes under that is
Yeah,
okay.
exactly.
yeah.
And now, so sorry. You,
No, go on,
I've
go on,
taken-
no.
I've
But
taken
what's still
over.
like the relevance of this? Like, for me at the moment,
So-
it's cool.
It's
Yeah.
cool.
It's interesting.
So a lot of
That's it.
math starts like this, actually, doesn't it? It
Yes.
starts with like
patterns
just
and
like
stuff.
or just people like on the room. Like, oh, this is cool. I can categorize things in groups, and then you find an application for it.
Okay, applied maths.
So molecules, they have shapes and
Hey, should be on
symmetries.
that side now.
We're
like
talking
this.
about the chemistry, but
like
I'm
this.
going to jump back to you. And obviously,
Yeah.
because molecules have shape, you can categorize different molecules by their by the groups they're in.
Mhm.
So you have square planar molecules, and a square planar molecule essentially, I mean, you have different types of square planar molecules. But imagine one atom
Mhm.
that's bonded to 4 atoms, but all the atoms are in the flat.
Mm.
Okay, so it's one atom and it's got 4 corners. And if you look at it from above, it almost looks like a square, and it's flat. That's what it's called. Flat. It's square planar. Now I'll let you carry on. What are you going to say about square planar molecules?
That's lovely. Just listen to your voice.
I agree. I was mesmerized.
Yeah,
I wasn't even listening. I
carry
was listening to his voice. That's it. I'm messing.
Yeah, well, it's great because these have symmetries now.
Yeah.
So you already know something about it because if you rotate the square a little bit, it's the same thing. 90 degrees. It's the same as if you hadn't done anything to it at all.
Yeah.
And there are some like quantities in chemistry, like some really interesting integrals.
Mhm.
Which like, what would you call it? The electrostatic integration or something? Or the
what?
dipole moment
The dipole moment, yes.
of the molecule.
Yeah.
And
no.
you're far more equipped to tell, see what dipole moment is than me. But
So not all molecules have a dipole moment. So a square planar molecule probably wouldn't have a dipole moment, but it depends on what atoms are.
What is that? Is that too?
But it doesn't matter. So you know how so atoms have a nucleus
Yeah.
that is positively charged,
Mhm.
and then around them they have electrons that are negatively charged. However, some molecules, the electrons might be more concentrated on
Oh, in
one
a certain
side.
area.
Yeah.
Isn't that with the water molecule? It's like,
Yeah. So
Yes.
water
Yeah.
molecule, because the oxygen atom is more electronegative,
Yeah.
it withdraws. It's more negatively charged. It has more electrons around it
Yeah,
than the
it's like a
hydrogen
partial
atom.
positive side, partial negative.
Exactly. That's exactly what it is.
Gotcha. Yeah.
So for the general audience, the oxygen atom is more negatively charged. The hydrogen atoms are more positively charged. Remember, water is H2O, so it's an oxygen with 2 single bonds to hydrogen atoms.
Yep.
Because that difference in the concentration, shouldn't say concentration really, but the spread of electrons throughout the molecule, that creates a dipole moment, or
Gotcha.
which
Yeah.
means like a difference in the molecule.
Mhm.
If you had just O2, because they both have the same, amount, the electrons are evenly spread out. There's no dipole moment. There's no like difference.
Yeah. It's
You see what I understand?
all around. Yeah.
So carry on. What were you going to
so yeah, and we again your voice.
say? Thank you.
Amazing, isn't it? I know. You should come more often.
So we can calculate this dipole moment by like an integral, like a fancy operation.
Yeah.
Which is
He can do that a lot better than I can.
it's quite complicated.
Yeah.
And suddenly we would look at this operation like, well, it's quite hard. And by quite hard, I mean really, really difficult. It will take ages to do. But then you start saying, well, hold on. The molecule in question has a symmetry. So we could do this thing to this molecule. And now this integral is suddenly a lot easier to solve. So we could apply like a
That's
rotation.
amazing. Yeah.
And say like you're integrating something in like some weird space over here.
Yeah.
You apply a rotation, suddenly it's flat on the plane. And
Yeah.
that's kind of hard to intuit, like what I'm saying, because it's like, what is integrating over here look like? I don't know.
Yeah.
But then suddenly you can transform into something which is nicer because of these operations, because it belongs to this group, and because this group, this object itself is well studied.
Yeah.
It then applies directly to the molecule in question, and then you can say without any complex calculation, yes, I know what the dipole moment is.
Gotcha.
And
based on rotating and calculating it somewhat easier.
Or based on the symmetry. So remember, the O2 molecule doesn't have a dipole moment.
Yeah.
But the O2 molecule is way more symmetrical than a OH2. Remember?
Yeah.
If you because it's just an oxygen and an oxygen.
Yeah.
That's a cylindrical axis of symmetry. And that somehow that corresponds to the dipole moment. That it doesn't have a dipole moment because of how highly symmetrical it is.
Yeah.
Another symmetrical molecule, the very symmetrical molecules, one have a dipole moment for the same reason.
Yeah.
And some groups, and so that tells you that, okay, all molecules that are within this group are never going to have a dipole moment. And all of the ones with this group always will have a dipole moment.
Yeah.
So that just simplifies the work so much.
Yeah.
Already.
So that's
you
the
just
way
have
of
to
like
work out the
applying it
group.
into...
You work out the group and you automatically know.
Yeah, exactly.
Yeah.
And there's a process to figure out the group.
Yeah, it's like a whole tree diet you do.
We've probably seen the same one, haven't we?
Yeah. we had it in our data sheet on it's so important as well.
Jamie, pull it up. No, but I think like it's very interesting. And essentially, the hard work is figuring out where it falls under, and then you can figure out from there. What about with circles?
Circles. Oh, how many axes?
That's what I was gonna say. Isn't
reflection
it like,
does a circle have?
Infinite?
Yeah,
Yes.
exactly.
Yes. So it belongs to a different type of group.
Entirely.
It belongs to a matrix group.
A matrix group.
And
Okay.
then this is when we start getting a bit weird.
This is beyond me
This
now.
is more like the more
Yeah. So
the
what is it?
uncharted territory.
Special orthogonal group?
Ooh,
No?
that's yours.
Special,
Say again?
Special orthogonal group?
Special orthogonal.
Well, orthogonal just means like... carry on.
No,
Sorry.
keep on going.
No, you carry on. Because I'm not going to explain it well.
Well, this is good. So this kind of relates back to the sphere we're talking about. It's called SO2. And do you know what a matrix is? It's like a generalization of vectors, right?
Yeah, a lot of people are not going to even know what a vector is.
I know Matrix is a movie, and that's it.
This is a very... My mom watches this.
So does my mom.
Yeah, exactly.
See, this is the thing, though. This is it's like survivorship bias. But for so long, I forget. It's not meant to sound like a flex.
Not many people even know what survivorship bias is. But what you're trying to say is because you're so into it, you don't understand how. But that's why we're here.
But here's the thing: I'm going to say the sentence now, and then you can look at me confused and tell me to shut up.
Yeah.
But I think that's a wonderful experience because when I say that the symmetry group of a circle is SO2, and that relates to rotations in 2D space, the natural extension of that is rotations in 3D space, which are quaternions. And you think to yourself, oh, quaternions, that's amazing. That's an extension of the complex numbers with less structure. I think they're not associative, or whatever the correct word is. You think, what? How is this thing, this algebraic quantity, now related to this geometric quantity? And it's something as simple as what is the symmetry of a circle? You can just ask yourself these questions, dive into that rabbit hole, come out of it 4 years later, and end up on a podcast.
Literally, yeah.
Sorry, carry on. You carry
No, I
on.
was gonna say as a quick random segue. I was saying like I really see what you mean about how in your position, with the knowledge you have about maths, it's hard to speak about it and not really remember like the level that the other person knows because you only know what you know, if that makes sense. Yeah,
exactly. My lecturers did an amazing job of this.
Yeah.
They're probably sick of me by now. I was telling them how, well, this is kind of terrible. I wrote an application to join The Apprentice.
Oh, is it? Oh, yo. Really? Damn. Yeah.
I had the interview yesterday. It didn't go. They gave me. They put me through to the second round.
Oh, bro, this guy
yesterday.
Yeah, yesterday.
No way. That's so cool.
Yo, breaking news on Knowness. The vault of knowledge.
The thing is,
if you win The Apprentice, are you going to come back for a podcast?
Yeah.
Okay,
yeah,
great.
please do like a
We're going to have
podcast
you back.
podcast,
Yeah.
Yo, extra views.
The thing is, and I know they're going to do a background check on me, but it should be fine. And I don't plan on winning it. I don't.
Is it? Yeah,
I don't even plan on going. I want to get fired.
I feel like you'd be smarter than most people.
Nah, dude.
Bro, come on. You're gonna be
It's
more.
easier
You're gonna believe. You're gonna have the
mathematical
grit. You're gonna have the grit.
I'm not an asshole. I can't be like terrible on camera.
Yeah. You kind of have to be for this. Yeah.
There's like that. they're looking for like subtle misogynists, and people who are really cocky.
Yeah, that's what makes good content. You know what I mean?
Yeah, I don't make like I'm not gonna make the most amazing TV out there.
Yeah,
Someone's gonna say, "What's your business plan, Mavs?" Or, like, I don't have one. I just did this for laughs.
Oh, that'd be good. No, that's good content in and of itself.
Yeah,
the maths guy is too overqualified to be there.
but I was kind of hoping maybe they can pull the posh mathematician like angle. It's like you know, someone sees this guy. Look at him. He did maths.
Yeah.
What an idiot.
Yeah. And you put up and like mathematically describe how you're gonna win.
Oh, yeah. I'll sit down in boardrooms. Lord Sugar, this is statistically impossible. You're fired.
Yeah. There and then. Yeah. Let me explain the mathematical theory of your pen. Of the pen, like you do with the globe.
Well, it's interesting. When I watched Wolf of Wall Street, I never understood that question.
Yeah,
it's like you got to make someone want to have your pen.
Oh yeah, the settling the pen thing. Yeah. There's so much applications. Yeah.
Going back to maths.
back to maths.
This is not the entrepreneurship series. This is the knowledge series, bro.
You can see how varied we are.
Yeah, exactly.
It's crazy.
Math
is everything.
Broad.
Yeah. Even like the medical side of things is insane.
I was really curious. You know, man, you said that sentence so complicated and stuff. I was thinking that would be so much easier to explain to someone if they could just see a couple of drawings, because we can innately see really complex mathematical concepts by just looking at the objects that they're meant to represent. You know what I mean?
I see.
Like I could just show you a circle and a sphere, and you'd be like, you can see like what the similarities
when you described
are.
it with the axes and stuff, it's easy to imagine because I know what a square looks like. I can picture it in my head.
Yeah. So, and that's something that was nice about chemistry, because we always are looking at things.
There's always diagrams.
So we always have like a diagram and stuff.
It's like maths with pictures. Is that chemistry? Is that your definition of chemistry?
And
maths with pictures.
Yeah, and I wish a lot of maths education was more like visual, more picturesque.
Yeah.
Wow, it says funny. I don't know if you're just baiting me here. There's this thing I worked on. It's called Visual PDE, Visual Partial Differential Equations. You know, I was talking about Alan Turing, how he has intuition to produce these equations and figure out these like systems, how they would evolve. So in the last 20 years, when we solve these equations, they used to get supercomputers to do them, like in like 1980s. And those would take maybe a few minutes or a few hours.
Yeah.
And then as technology improved, we could start using our laptops, our PCs. And all that meant is you had to write like some custom code, and it'll take maybe 2 minutes to run our software. And this is kind of what prompted my kind of love for math bio, was this product, Visual PDE. I worked on a prototype partial differential equation solver, very hard to solve generally.
Yeah.
To numerically solve them on common devices like your phone or your laptop. And
so just a note on wording. When you say numerically or generally, is that the same thing as saying analytically?
Sorry, yes, no. If I meant generally, when I say generally, I mean you can't solve them analytically.
Okay,
yes.
okay, yeah.
So instead, we solve them numerically.
Okay, makes sense.
And by analytically, I mean there's no closed form expression, for instance, the quadratic formula.
Yeah.
So yeah, what we do there is we solve these things numerically very quickly.
Sorry, I'm interested in this. So when you say numerically, is that like an approximation or is that an actual solution?
It's an approximation to a solution.
It's an approximation. Yeah.
So yeah, the idea being that a computer can do like operations very quickly.
But they can approximate a lot better very quickly, essentially. And because solving it properly, let's say analytically, would take.
Well, you can't.
Or you just can't do it. So it's like a man.
There is just no
like a three-body
solution. Kind of like that. Yeah.
Because my master's was in like modeling. It was in computational chemistry. So this is exactly what I was doing every day for a year. Yeah.
Oh, you missed out on Visual PDE. Visual PDE basically took this thing. There's these processes which took supercomputers hours. Yeah. And we managed to get it running on something like a smartphone instantly.
Normal everyday devices.
When we got the paper out, that's pretty much like the first line.
So how does it do that? So it's still approximating.
It's approximation, but it's a good approximation.
Yeah. But it's using what?
It's used. So we use GPUs, so graphics processing units, on the devices to parallelize these time stepping methods. So very often these methods are done on like a single thread or a single core, which means you're waiting for the entire thing to update. But instead we used like the distributed architecture of a GPU.
Yeah, this is quite new because I heard about this in chemistry as well, using graphics cards instead of do exactly what you're saying.
Distributed processing has been like a big deal recently.
So that was really interesting. So how do you, when you're doing approximating, so I don't quite understand. So how do you do, like, so you have multiple steps happening at the same time? So how do you know that steps are talking to each other, if you know what I mean? What
Yeah.
if you have diverging steps?
Each pixel, so diverging, good word.
Yeah.
When we approximate, we're approximating the derivative.
Okay.
So dy by dx
Uh-huh.
is like, it's like a continuous thing for us.
Yeah.
But on a screen, you actually have pixels. Pixels are discrete. You've got 1, 2, 3, 4, 200,000.
Yeah.
Uh-huh.
I don't actually know how many there are.
It's a quantized number of pixels.
Hey, I remember that from his last podcast.
My last podcast, he loved that
Quantized.
word. He was quantized. Wow.
Nice word, quantized.
Yeah.
There is a number of pixels.
Quantized them out.
Yeah, it's a quantized.
And we basically have, we let each pixel update pretty much independently. It looks at the ones next to it.
Okay.
But that's the point of GPU. It's spreading out the processing from one core to thousands, which makes things go way, way, way quicker. And you can approximate the derivative by like some small constants. And the smaller the constant, the better the approximation. And because it's so fast, you can make this approximation quite good. And I won't go into too many details because, read the paper.
Generally, why are you approximating exactly? Like, what is it? The application for it?
Well, it's so you can solve these equations rapidly,
which are used for everything. All sorts of things.
I mean,
like in chemistry,
it's pretty much.
This
isn't used across the world in various universities. So Sydney are using it in the math bio course. All of UCL's math bio department are using it. All of Durham are using it. All Oxford are using it. Cambridge are using it. Like you speak to lecturers, they have heard of it. They're using it because it makes their life so much easier. It's like when you were a kid and you had to write your first essay. Wikipedia is just there for you. You don't have to go to like 20 different sources.
ChatGPT now.
ChatGPT now.
That's massive then.
It's
It's
like
one of those
that.
massive developments I just don't, everyday people just don't really know about.
Of course. I mean, why would you? You don't even need to care about Visual PDE.
Yeah,
but
literally,
It's people like in this field who know it and love it because it's incredible.
But again, this is why is the visual aspects of mathematics that really always surprises me. Is how we have an innate ability to recognize symmetry like instantly.
As humans.
Humans, we're just innately born with the ability to recognize objects and see the symmetry visually.
The symmetry.
But when it's just explained to you in words and stuff, that's when people get confused and stuff.
Yeah.
But you're now subject lead. You're in education, maths education, and you're working on some of our content. So how are you gonna? Do you have any idea how you're gonna approach it to try to change the way traditionally maths has been taught, and maybe what are some new techniques or approaches?
We have a normal GCSE course. We also have a general learning for maths. On Knowness.com. So tell us about that.
I like to call myself a very stupid person, and that's how I've gotten this far. So I'm gonna when I have the maths, it's gonna be to the lowest common denominator. And that's me.
Good maths joke.
Yeah. It's not a maths podcast, a little maths joke.
That slide. What I want to do is with each of these, like let's start with the taster course, for instance. I want to pick something which is sexy, something that you don't ever get taught at A level, or even until second year of university.
Wait, hold on. But do you want to explain what the taster course is first?
Of course.
The taster course, is that available on
Knowness.com?
Sorry, continue.
I'm currently working on it right now.
Add Knowness app on Instagram and all social media. Sorry.
All social medias. And LinkedIn, TikTok, YouTube.
No, carry on.
Sorry.
There's one more. Instagram.
I
think that's it.
Twitter.
So yeah.
Twitter. That no one uses.
What was it?
Sorry, carry on.
It's
Just being silly.
The taster course is kind of designed to help make people understand what university could look like when studying a maths degree. And what I want to do is really like emphasize things which you aren't taught at A level and kind of get across the idea of mathematical thinking. Because I think maths at GCSE and A level is computation. It's not fun. It's not sexy. It's go home, do this calculation.
I kind of enjoyed it, but fair enough.
I mean, when you really get into the nitty gritty of it, you're like, oh my god, you can do this.
That's the thing. I feel like I've never really like learned or really had like mathematical thinking. Because for me, it's always just been here's a way to do it.
Yeah,
you do it, and then that's it. Like A squared, B squared equals C squared. What is that? Pythagoras?
Yeah, Pythagoras.
Very good.
You can ask so much better questions. That same thing leads to what's the shortest distance between 2 points?
A straight line.
A straight line.
Yeah.
Why?
Let me think about it.
No, it's a hard question. It's
well, I feel like it's just that there's no like How do you describe that? I know it makes sense in my head, but
There's no other path.
yeah,
which-
you're not wasting time in the other paths.
So it's like an elimination thing, kind of.
Yeah, and the hard task is to prove it. That's mathematical thinking.
Oh shit! Yeah, that's like
What's the shortest distance between 2 points on a sphere?
A line still
Is that a line or is it a great circle?
between 2 points.
Yeah. So if you have
Still
to
a
travel
line.
the surface of the sphere,
Okay,
then it's an arc of the sphere.
it's an arc. Okay, fair enough.
And then
Yeah.
Is it still not called a line if it's if the space itself is curved? What will you say?
well,
Because if you, let's say you are someone who exists on a sphere, would it still be a line? I don't know. You tell me.
try telling me. I mean, I see what you mean.
Wait, do you mean
Yeah,
from like I don't know,
Like it's an arc.
random
from-
country like Libya, from Libya all the way around to Libya.
Yeah.
What do you mean from like Libya
That's
to
the
like
circumference.
Russia?
Yeah.
Yeah. Okay. So that's a different thing actually.
That's the
That's
circumference.
that's
yeah.
locally.
Not the
it's-
circumference.
what we're saying locally, it's flat. Right?
Yeah.
So locally, it looks like a straight line. So you zoom in, you'll get a straight line.
Yeah.
But globally, it's curved.
Gotcha.
So that's something else.
Yeah, don't worry.
So this is what
It's
you're.
an arc. Yeah.
Yeah.
Yeah,
So
carry on.
I'm just saying it's like an arc is not the same thing as a straight line. I should say. I'm being hand wavy here, and then you can ask yourself the same question: why? And that's a proof of
there's there's a way you can mathematically like prove it definitively.
Yeah.
That's what I want to
Yeah.
emphasize: mathematical thinking. I
Yeah,
want to
'cause I
give
don't get that. Yeah.
like a chance to look at something like an interesting result and say and make people ask why. And if they want to ask why, they can look at something else, and there'll be references for that. But primarily, just gives them something which looks cool, which they won't be taught at A level or further maths. Like for instance, knot theory, right? Knot theory has applications to mathematical biology. Funny enough.
Like DNA and stuff. That's
yes.
very important for DNA.
Exactly, DNA like hypercoiling.
Oh, not theory. What's that?
Not theory.
So like tying your shoelaces, right?
Yeah.
If I give you like a loop, and then ask you say something weird, if I make a cut here, how many cuts do I need to make to get back to a perfect loop?
Yeah.
Yeah.
And then like linear algebra, like the textbook course for everything you're going to do at university, we just don't have that at A level, not done properly. Like Google PageRank, that is the $1 million eigenvalue problem. And well, someone's going to look at me and say, what the hell's an eigenvalue? And then I'll spend 2 years teaching them maths.
The thing is,
That's-
eigenvalues, as I was saying this earlier off camera, they're not even difficult concepts, really. They're way easier than a lot of the maths we do.
But maybe there's some survivorship bias.
Okay, yeah, fair enough. No, okay, fair enough.
Yeah, I was gonna say.
No, I get it though. It's like they're so nice, like really cute objects. We use them all the time.
Yeah.
My Math Bio, third year Math Bio course is basically a course in linear algebra.
Yeah.
It's just dressed up to look like Math Bio.
But if I say if you were to go back in time, and you were going to do go back to university again, would you have done natural sciences still, or would you have gone straight to maths? It's a bit of a difficult one because
I think about that a lot because I'm going into neuroscience now.
Yeah, so it's like
often
if you
think-
went into neuroscience instead. Like I don't know. I think for me, I would have still done medicine despite knowing everything and and all that. But would it still be natural sciences?
I don't know.
Yeah, it's a hard one. I don't know.
It's hard to say because like you got to this point doing natural
Because of
sciences
it,
first.
yeah.
So maybe you wouldn't have gotten to this point if you did
just did
something
maths.
else.
So maybe
Maths
if you did
was-
maths, you would have been like, I wish I did natural sciences.
All right, stop talking. Let him answer.
Answer for me, please.
Yeah.
Give me no. I think I can. That's what I know. But maybe I would have done like different modules. Maybe I wouldn't have done chemistry my second year. Maybe I would have known COVID was coming.
Yeah.
Oh, bro,
That
don't get
was
me started on COVID.
different.
Oh
No.
my
Just-
days.
Let's not talk about it. We can't say that on the podcast. Yeah.
Yeah.
But at the end of the day, my third and fourth year were quite solid when I knew what I was doing. I ended up doing a bit of earth sciences, and it was like fun talking to the geology boys. 'Cause I could walk in.
Everyone likes the maths guy in STEM.
They
'Cause
did. They loved
everyone
the maths
loves
guy.
the maths guy because you can talk about all the subjects. You
They
always have
study
something-
rocks.
Yeah.
Well,
Ionic lattices and stuff. They're like, oh, yeah, fair.
they're a funny bunch. But yeah, like
Yeah.
I don't know. Maths was probably like the thing I was going to do. I didn't realize it at the time. Would I have done well before that? Would I have known that I wanted to do maths A level? Maybe.
Yeah.
I think I should have done music.
Yeah. Really?
Yeah.
That's so
Well,
that's
that
really different.
goes very like closely with maths.
I was gonna say I can imagine it probably does. Yeah.
Yeah, it's one of those things like
Yeah,
no matter where you are in the world, there's a 5-year-old who's better than you.
Yeah.
No matter how good you
Yeah.
are,
Yeah.
I could find someone who's better than
Just
you.
5 inches back. Yeah.
And once you get over that
Certain
thought,
regions of the world. There's a lot of-
No comments. No comments. No comments.
But carry on with the music in maths because I'm really interested because I'm gonna go in a bit of a tangent there.
Yeah.
But so as I said earlier, visually everyone has an innate ability to understand maths and they can even appreciate the beauty of it. Everyone loves symmetry. Everyone loves patterns
This is nice.
in nature. We all like naturally resonate with them.
Aesthetically pleasing.
And when music is now instead of visual, it's maths, but that you can hear, and it literally moves us just listening to maths. Yes, it's like a semi-regular pattern. That's what makes really good music.
Yeah, it's like listening to
It's just about when it's like a mixture of a very recurrent, very continuous pattern with just the right amount of randomness in it.
I can't even describe music. It's something. It's magic to me.
Insane.
It's so complex. I looked. There's some mathematical books on music, and
music theory is very complex. Famously,
it's tough.
Really?
They use some group theory stuff in music theory.
yeah, it's insane.
Yeah.
It's insane.
Beyond me. Like it's insane how it exists. The thing is, though, this is not maths, but what I find with music is that it's one of the few things where you can understand something about someone without them even like saying a word. My desk partner in one of my orchestras, she's a cellist, and this is going to sound so pretentious and so arsey, but we did a duet together.
Yeah.
She was playing the piano and I was playing the cello, and I literally felt like I could read her mind. I was like,
from the music.
Yeah, because I was like, hold on, I'm going to play a lot louder here. I'm going to speed up, and we're going to play it. It's going to be so much more ferocious, and she's just already there.
Yeah.
Like, how did you know to do that?
Yeah,
because you just felt it, and we weren't saying
anything. It's like
anything.
talking without talking. Yeah.
And the people who were watching our flatmates, like, wow.
Yeah.
And then I played a wrong note, as you do. But there's lots of maths and music, obviously group theory stuff. And one of my favorite theorems comes from that. So, have you got any pianists?
No, I know Eddie.
Fruit Loops.
It's so you can imagine like the piano keys, right?
Yeah.
There's a fun theorem which basically says the number of intervals. So like 1 note apart, 2 notes apart, 3 notes apart. There's the same number of the same type of intervals if you partition a octave into 2. Now that's a bit abstract and vague, but basically if you take a octave on a piano, which is 13 notes, and you cut it in any 2 partitions, so like it's got 6 notes, so let's say 12 notes, so it's got 6 notes on each side, then there's going to be the same number of minor thirds, same number of major seconds, same number of perfect fifths, same number of perfect fourths, and so on each partition. And to me, when I found that out, I was like, "Wow, that's insane. That's just a weird thing." And you can like look at it on a piano. You can just see it by playing around. And music and maths, and it's got some applications elsewhere which I've already forgotten. And it comes out now. It comes out like the discrete Fourier transform, which is funnily enough used in how these microphones are recording my voice. There we go.
Fourier
transform. 2 things which are different are the same.
That's crazy, man. It's crazy. Like it's maths and like it's in music. We talk about in biology, chemistry, computer science.
Yeah, we use Fourier transforms in chemistry
medicine.
all the time. That's such an important like imaging and stuff.
Because I always like growing up thought maths is its own isolated thing, but like it's everywhere, man.
That Fourier transform comes from the war as well, don't they?
Fourier?
Yeah. It was like a World War II
during
thing.
World War II.
Joseph Fourier? He was
Fourier.
1600s, I think.
Oh, was it? Where do Fourier transforms? No, it was a solution to Fourier transforms. I think that's where it came from. World War II. Never mind.
There was a guy who found a solution to a black hole equation in the trenches of World War One.
World War One, not 2.
Was it World War One or World War II? I can't remember. So
that trench foot is just
he was being bombed by artillery. I was like, yeah, let's do some maths.
Probably shook his head a little bit. And he was like, wait a minute.
That's shocking his bit.
You imagine the shells coming down. You think, yeah, I want to do some general relativity. Let's show Einstein what for. I mean, that's incredible.
It's insane, man. There's people out there like that. Well, used to be.
Were. Schwarzschild, I think that's him.
Yeah.
If you recognize, Schwarzschild
it
radius.
rings a bell. Yeah, it rings a bell.
Nope.
But again, when it comes to this is something I find quite interesting. So when it comes to like people, again, as I said earlier, I know a lot of people who hate maths. When it comes to, because a lot of them have like a humanities background, how I like to approach maths to them is I try to show them like historical examples. So like the Greeks solving the Pythagoras theorem, but then like Native American civilizations also doing their own solution for the Pythagoras theorem. And that's what it kept them going. It's like, oh, you can see the Egyptians doing a similar thing. So can you tell us a little bit about maths history, like where, if you know a little bit about it?
Maths history.
Because I like talking about the history of quantum mechanics, for example, in our podcast. Like where the different ideas come from. We got Newton, very important.
Oh, yes.
And stuff like that.
Yeah.
So like the calculus guys, and they discovered it at the same time.
Exactly.
It's really interesting, maths history, because we kind of taught it all at once.
Yeah.
And I forget what,
The
it's
history of
4,000 years
maths
old.
or just maths, like all the
Well,
maths?
the history, like the maths which comes from the history. So
Yeah.
Pythagorean theorem, 4,000 years ago.
Yeah.
Um,
But were they the first ones was Pythagoras the first one to discover it?
no, is it maths discovered or is it found?
Yeah, exactly.
Is it created?
Founded, really.
Yeah,
it's not
yeah,
really.
yeah.
I mean, discovered and found is anything. You mean invented? or
Invented,
found?
sorry.
Yeah,
Invented, yes.
yeah.
I can't tell you probably about the history. I really wish that definitely something I should think about. There is a book called The History of Topology. It's like 200 quid though on
Oh
Amazon.
my days.
That it goes into it like beautifully.
Yeah.
The also architecture for me is huge when it comes to maths.
Yeah.
You've seen like sort of like mosaic patterns, especially like in
old,
in like
Spanish or Arab, like
architecture.
architecture.
Like in mosques as well, but also in churches as well. Like incredible.
There's a good
very
paper
cool.
on aperiodic Einstein tiling of the plane, which was released last year.
I think so. There's the
Yeah.
Penrose patterns as well. Then is that a different thing?
I think that's related. Yes.
Yeah, it's related.
Yes.
Yeah, no, as growing up, I always thought, going to university, doing maths, what would you do with a maths degree? You become like a maths teacher and then that's it. But
I
like,
always
clearly it's just a lot more than
Yeah.
just, yeah.
Really?
There's loads.
Yeah.
I always thought maths was seen as like a very employable degree.
But
I thought so.
I think these are two schools of thought
Yeah.
where
Yeah.
you've
see it as like a
used
skill.
maths, right?
Hmm?
You've used maths
Yeah.
for the last.
Yeah, so I feel like you have that view because you've had the application of maths. I've
Oh,
never
fair
really
enough.
applied it. I've only ever seen it as, what job can you get by knowing the quadratic formula? You know what I mean, that's how I've seen it in my very like limited,
Because like
shallow
there's
perspective.
like finance jobs. There's all these data
Yeah, but
jobs.
a lot of those,
They're
like-
all mathematicians, aren't they?
Yeah, but it's like maths application.
Okay.
But again, we never really did that
Yeah.
I never did. Even with your job as well, you said it was with
I work with Nest. They are the biggest company you've never heard of.
yeah. And the second biggest company you've never heard of is
Not for long though. Not
Only
for long.
We gotta
Not
rock
for
on.
enough for long. No, we'll get there.
Yeah, no, it's really interesting stuff they do. It's like basically securing the retirements for low-income earners across the UK. So it's an automatic enrollment scheme, and they've hired me as a data engineer. They didn't hire me because I could do data science. They hired me because I had a maths degree.
Yeah,
And a maths degree, and what I've used it, I've not used differentiation or calculus.
Yeah.
I've used the mathematical thinking.
That's exactly it.
Mm.
Yeah.
And people go and ask you what's mathematical thinking. That's saying, here's a problem, go figure it out.
Yeah,
Problem solving, but it's very.
very.
It's like the meta
strong
problem solving. Yeah.
Yes. And people say on the
In-depth problem
CV
solving.
or whatever, I've got problem solving skills. Everyone says that. Your maths degree confirms it.
Yeah.
Yeah.
It's signposting them towards your abilities.
I feel like I should have done a maths degree now. I think about it.
Then I've done my job well.
Yeah.
But like you can go anywhere with it, and that's the problem.
Problem?
Well, because you don't know what to do.
Yeah, that's true. I think
It's a
very
good problem to have.
No,
Not
it's
gonna
very
lie.
clear-cut.
There's worse.
I mean, I went into teaching for 1 month. I only lasted 1 month because a kid tried to stab me.
Like teaching, like, oh wow. Where were you
That's-
teaching?
I don't know
Birmingham?
what is
Don't
going
do
on.
this to your teachers. I was teaching in Tunbridge Wells, right? You think
Yeah.
Tunbridge Wells, the home counties, what? The worst postcode in Tunbridge Wells.
Oh, wow.
And I gave it a go. The kids were lovely, but they didn't have the greatest home backgrounds.
Oh yeah.
And I remember this straight after I graduated. I didn't like them,
The kids.
but I understood them.
Oh,
Because
okay.
they tried to stab me.
Oh yeah. Fair
It
enough.
was 9 a.m. I didn't have my tea yet, you know?
But the stabbing thing is, I'm still stuck on this. What happened?
Yeah, well, you got a pair of safety scissors, by the way.
Oh.
They weren't even going to do anything. Like, I'm not a hard lad, but come on.
Yeah.
How old was the
insane.
kid?
He must have been 14 or 13.
Okay.
But does it matter?
No. I'm just like,
But like the thing is, like,
if he was like 6, I would be like, wow.
Yeah.
troubled child,
Yeah.
obviously, and I feel bad for him that it was his reaction to do that, because I think I just got his name wrong and he got frustrated.
Yeah.
And like obviously it sucks, and there's more that could have been done before it got to that point.
Yeah, leading up to it.
But when I was in that school, and it was very low performing school, I was given the chance to do a lesson. The teachers said, I don't want to do this. Like, Alex, you take over, because they knew I had a maths background. I was the only person there with a maths degree.
Gotcha.
And they just said, oh, have at it.
Yeah.
And that was the one time where I could get a class of 20 undiagnosed kids, all with ADHD, to sit down and be quiet, because I told them about, the speed of light, general relativity.
Yeah.
I said the same thing about the straight line.
Mm.
I showed them the Euler Lagrange equations. They were like, oh my God, what is this? This is real maths.
Yeah.
As opposed to add up these two numbers together.
Which I think in a teacher, I'd love that. Someone actually cares, you know what I mean? And tries to get you to have that mathematical thinking.
I also swore a lot.
Okay.
Yo, those are the best teachers.
You're not allowed to do that here, but
But okay, one thing I was just thinking of now as well is, you ever see like the movie by what's that director?
That guy
Fantastic
that-
Mr. Fox.
hey,
Oh, I know that one, yes.
What's his name? The one who did Fantastic Mr. Fox. Wes Anderson.
is that the one? The symmetry,
Anderson.
everything is
And
symmetrical.
exactly. The reason I mention it is because in a lot of his movies, I love watching them because it's so
French
like,
Dispatch,
it's just
especially. That one is really
that's a good film.
exaggerated. Yeah.
It's just so aesthetically pleasing, you know? It's just nice on the eyes and on our minds to see all those symmetry and everything. So what I want to ask now is, you've spoken about how like maths kind of comes into medicine and chemistry and all the subjects. But when it comes to the creative arts, movies, arts, talk to me about that. Because that's something I find
That's
really
a very
interesting.
good segue to what it says on the on the prompt.
I'm not going to look. I'm going to be surprised. How does
I think it's such a sly way.
That's such a good segue. I could not stop.
being so
It
sly
literally
with
says, ask him if there is any maths in entertainment creative arts like film.
Creative arts like
It's such a good segue. Well done. You're very good at your job, man. Yeah.
Thank you.
Give that to you.
Now you ruined it. Anyway.
cut.
Restart. We're on.
The producer's gonna have a word with me afterwards. I know this.
Hey, if you never see this guy on again, now you know why. Anyway, talk to
Maths
us about
in the
that.
arts and humanities.
Yeah.
Funnily enough, I'll name drop him. Dr. Adam Townsend wrote a course for this.
Shout out that guy.
He's
Shout out
a legend. He's
Shout out that guy.
he was in UCL when he taught this course. I think it was UCL, and now he's up in Durham. There's plenty of overlap, so that's also a good one. What are you saying, like arts?
Yeah, so in arts, in like
So he
different artworks,
means
you
more,
see.
that was an example of cinematography more than anything. Yeah.
The Wes Anderson movies and also cinematography, but in general, we have arts, movies, films.
Well, let's give a good one.
We
Yeah.
did speak about music. That's one form of them. What about like the other forms? Like
This is
movies?
gonna be a good example, I think. Let's say video games.
Yeah.
Maybe it's not necessarily arts.
No, it is. That is arts. Technically,
Hey,
it
that's
is.
not for me. That's my expertise.
It says
Wicked.
arts and entertainment there.
Um,
Carry on.
That's for me, not for you.
Sorry.
I'm just not reading it.
Yeah.
Video games, they do a lot of like rotations, right? You don't necessarily see it, but like when you rotate your camera
Yeah.
and you move your
Yeah, yeah,
perspective.
Yeah.
So that's a 3D rotation in space. There's a mathematical background between those 3D rotations in space. That's actually what I was talking about, the special orthogonal group. So there's an analog for this. This is called the 2-sphere.
Yeah.
It's called S2. So we look at something called like a projection of S3, which is described by quaternions, which are generalizations of complex numbers.
He got all
Again, I'm saying all this just to give a sentence of what and they use this mathematical structure, something which looks like a hypersphere, so something in 4-dimensional space, to look at rotations in 3 dimensions, and that is what's used in like video games. I can't go into too much detail because you'll like shoot me.
But if you're listening to this, Google it and actually put that into ChatGPT and ask him to send you links for images, and it'll make a lot more sense.
Exactly, you can visualize rotation.
When you can actually see it, it's actually not that difficult. Yeah.
I was just thinking, because I think I saw a video on this ages ago and I found it so interesting. Maybe you feel like Dark Souls.
Oh yeah.
Yeah.
Oh, yeah.
So there's a thing on like how the music, the boss fight music, And the attacks of the boss are kind of in time with in beat with the music or in sync.
I know exactly what boss you're
Something
talking
like
about.
that.
Batty video?
Yeah.
That's so. It's so interesting. Like, and
That's really
I guess
cool.
that kind of links into it a little bit.
That could be mathematical. You could actually just write it down. You could show.
I mean, it's patterns again.
Yeah.
When the beat of the music is, when and how like the length of the attack is for each boss, for each what's it called, swing.
Yeah.
That could be a good way to write something down. Obviously, I don't have a pen and paper right now.
Yeah.
I can give you the world of a pen and paper.
Yeah.
But there's plenty of examples. So, I mean, I gave you video games, and we're going on to that. But then we've talked about music already.
Yeah.
I guess like fine art is the next thing. I haven't really looked at that. Again,
I mean, well, I give the example of architecture.
architecture.
Yeah.
That's basically fine art. It's like visual, like the geometry.
When you say architecture,
patterns.
I'm now thinking engineering.
No. I'm thinking like, like pretty buildings kind of thing.
Yeah.
Like mosaic patterns and stuff.
Oh, of course, like tiling.
Like tiling,
Yes,
exactly.
yes.
Yeah.
Exactly. Yeah. So even looking at this floor, we've got.
This is not a
tiling.
very interesting.
It's not an interesting floor, but
Yeah.
it's still mathematical, right?
Yeah.
We've got a shape, a very boring shape, but it's a rectangle. We can keep it,
These
plane.
walls are pretty interesting.
These
fair.
vaults, these
Bloody
old. They're very cool. I like them.
Have you heard of the moving sofa problem?
No.
The moving sofa.
So let's imagine that we've got a sofa,
Yeah.
and there's a
Left
door
two.
over there.
Yeah.
The moving sofa problem is how to get this sofa through that door. And what if the door is
You have to do that every day.
Yeah.
Every Sunday, sorry.
What if the sofa was wider? Can you do it every single time? What is the largest area of the sofa
Yeah.
that you can get to
Through
fit
the
through a
door.
door?
Okay.
And you end up with some pretty contrived sofas.
I think I've heard of this. Yeah.
I won't go into the full thing.
It's
but
like all weird shapes of sofas, which is trying to get the biggest area possible.
Yeah.
But like at some point it becomes
So
okay.
isn't
Is
that
that even
door-
a sofa
It's not a
anymore?
sofa.
It's not a sofa. It's more like any object that you can get through a door. Isn't
In
it?
one go, you mean? Or?
Yeah.
yeah, so
Like,
it goes
what's
in,
the biggest
that you can just
object?
rotate it around
Yeah,
the
yeah.
corridor.
Oh, I see. Okay, yeah.
It's one of those things like not necessarily arts, humanities, but
Yeah.
just an application.
Yeah. And I'm sure there's like more applications that come from
Yeah.
that you can use.
But like
Instead of just being like an interesting thing to just think
facial
about.
symmetry is really important
Mm-hmm.
in just in art, and also like if you're making a portrait, like the angle at which it goes
And the lighting.
and the lighting
Yeah.
and everything. That's really important. And getting those proportions right is what can make it look real versus look kind of uncanny. So artists are mathematicians in a way.
Yeah.
They have a very tough job.
Yeah.
Like, I am scared of musicians. I'm scared of artists because I just don't understand them.
Yeah.
And I guess that's probably how people feel about maths. If they don't understand it, it looks scary.
Yeah.
Um,
I mean, yeah, I think what is it with because we've only spoken for like let's say an hour or so, but already there's so much that it's kind of hard to wrap it up in a way. Do you know what I mean?
Yeah.
Because I kind of resonate with you when you say like maths itself is very hard to it's hard to like when it comes to communicating your thoughts and your what it's hard.
Especially without visuals or
Especially without visuals,
pen and paper.
So I don't even know how to wrap this up. But I guess that's one way of wrapping it up by just saying
meta.
that.
Yeah.
Meta,
Wicked.
Yeah. That's one way. But yeah, thank you so much.
Thank
It's
you.
been amazing.
Yeah, it's been
talking to
great.
you. It actually has been really
Yeah,
interesting. Yeah. Like I thought coming in like maths is just, we talk about the quadratic formula
Oh,
and
thank God we didn't.
Yeah.
that's a separate thing. But yeah. And then also thank you to my wonderful
Yeah, thanks for having me.
Yeah, who's causing me trouble.
Yeah, well, you caused me trouble on my podcast.
This is payback.
I just love this dynamic.
She's more often.
Thanks.
She's more often. But yeah.
Hopefully.
So thank you to the audience as well. And that audience as well. And we'll see you next time.
See you guys.
Bye.
Bye.
Bye bye.